Have you ever heard of Chladni figure before? It is an experiment done by Ernst Chladni, and it shows some of the interesting properties of waves, which is important in physics. If you haven't heard of it, this video will provide you with some insight about this. Now, let's start by looking at a few examples of the Chladni figures. A quick note, these examples are from the video done by Bruce Pop on YouTube. The link to the full video is available here. These are some examples formed under different frequencies. You should probably notice that there are areas that sand gathers together and areas that are almost empty. Also, as the frequency gets higher, the figure becomes more complex. Some of these phenomena will be explained later in this video. Ernst Chladni was an amateur musician who was educated in law at the University of Leipzig. This amazing experiment was first designed by him to make waves in a solid material visible in the 18th century. He got a metal plate, spread sand on its surface, and stroked the plate with a violin bow across the edge. He noticed that with different pitches, the sand on the plate forms different patterns, and he recorded all the patterns and published his work. So why exactly does the sand on plate form different patterns? First, we need to know some background information about waves. Chladni figures can be explained by standing waves. A standing wave is formed when a wave reflects off a boundary and interacts with the incoming waves, which is the original wave. All the points on a standing wave are oscillating constantly except for all the nodes. They are the points that don't oscillate and have zero amplitudes. A standing wave also has antinodes, that are the points with the largest amplitudes and have the largest movement. So applying this knowledge to the 2D Chladni figures, when the flat plate is vibrated, the plate oscillates not only as a whole, but also as parts. Instead of having points that do not oscillate, the Chladni plate has nodal lines, where sand on those lines are not vibrating. So when we put sand on the plate, sand on the vibrating part will move to the non-vibrating nodal lines, and thus, the oscillating areas become empty. Now that we understand a little bit about why the sand on a plate will move and form figures, there's another question we need to explore. That is, why there are different patterns with different frequencies. Standing waves don't form under just any circumstances. They require the energy be fed into a system at an appropriate frequency. That is, when the driving frequency applied to a system equals its natural frequency. Natural frequencies are certain discrete frequencies that the standing wave tends to vibrate in a system. All objects, including Chladni plates, have a set of natural frequencies at which they vibrate. When the driving frequency equals its natural frequency, the condition is known as resonance. Note that there could be lots of resonance in one system, and thus there will be many different standing wave patterns associated with different natural frequencies of the Chladni plate, and creating different figures. A plate's natural frequency depends a lot on the shape and support conditions on the edges of the geometry, as well as bending stiffness. And usually, higher frequency is associated with more nodes, and thus complex figures. Compared to a square plate that's shown in the previous example, the frequency of a circle plate is easier to explain using mathematical equations. The equation is shown here. F represents the frequency of modes of vibration for flat circular surface with fixed center. C and P are the coefficients which depend on the properties of the plate. M is the number of linear nodes, and N is the number of radial nodes. This equation is known as Chladni's law, and the frequency is positively proportional to the number of nodes. We can see that the more nodes it has, the more complex the figure will be. When it comes to the square plate, the equation becomes much more complex and is way beyond the content of this course. But the idea is similar to the circular plate, so we could predict the increasing complexity of figures with higher frequencies. I hope you learned something from this video, and thanks for watching.